Okay, so welcome to the afternoon session of this first day of our conference. We have two talks. The first one is by Akshay Yeleshpur Srikant from University of Oxford, and he will tell us about S-matrix unitarity and celestial holography.
Great. So let me start by thanking the organizers for inviting me to speak and to this beautiful place. So today I'll tell you a bit about celestial holography. This is the other kind of flat space holography. And the kind of philosophy we follow is we apply whichever form of holography is more suited to addressing specific questions. And one of the goals here would be to try to understand something about S-matrix unitarity and connect it to properties of the celestial CFT. So let me start by giving you a one-line summary of what celestial holography is. It's the conjecture that there is a 2D CFT which is living on the celestial sphere at null infinity, and the correlators in this CFT are dual to the bulk S matrix. I'll explain in more detail later on, but for the purposes of motivation, this should be sufficient. And roughly, there are two kinds of approaches to this. There's a bottom-up and a top-down. And in the top-down approach, you have specific models where you kind of know both ends of the duality, and you try to work with these, understand more about flat space holography. But the bottom-up approach, you only have access to the bulk. We know scattering amplitudes in the bulk, and our goal here is to deduce something about the dual CFT. We would like to understand some specific features of the dual CFT, starting from scattering amplitudes in the bulk. And because this might be a bit vague, let me, on the next slide, show you some kinds of lessons that were learned in ADS-CFT by a bottom-up approach. So one of the questions that was asked early on was, what CFT features are fingerprints of bulk, that of the existence of a local ADS bulk spacetime? And here, knowing that ADS-CFT can be embedded into string theory, one of the expectations was that semi-classically, when the ADS radius is much uh, larger than both the Planck length and the string length, uh, the, the, the expectation was that because the conformal dimensions are related to the masses, um, the conformal dimensions of high spin operators must be parametrically larger than those of operators of spin 2, for example, like the stress tensor. And this kind of expectation was confirmed by bulk perturbation theory, where you can compute ADS Witten diagrams, do a conformal block decomposition, and look at what arises. And another feature is that these ADS Witten diagrams give you something called a bulk point singularity. And what this means is this is a singularity that is totally not obvious from the perspective of a boundary observer. So if you're a person living on the 3D CFT at the boundary of a 4D bulk spacetime, this singularity has no business existing. And indeed, if you were to do perturbation theory at the boundary, you would never see it. And this arises as a strong coupling at the strong coupling limit in the boundary. But of course, these three features are not completely disjoint. One can start with a conformal block decomposition of the 4-point function. And this feature that the high spin operators have parametrically large conformal dimensions, this is essential in producing a divergence in this conformal block decomposition. And this feature that these higher spin operators are crucial to reproduce the bulk point singularity starting from a boundary perturbation theory. And so the lesson that we learn here is that the spectrum is intimately tied to some aspects of the bulk. And these are kind of the features that we want to see in flat space holography. But of course, I should mention this is work in progress, so I won't have very clear answers to any of these, but these are some of the questions that we try to investigate. And in ADS-CFT, there's a unitarity bound. And here things are simpler because the bulk time is the same as the boundary time. And if we ask time evolution to be unitary, you just get some bound on the conformal dimensions. Things are less straightforward in flat space times where, as you already saw, the boundary, depending on whether you are um, you're thinking about the 2D celestial sphere or null infinity, it's a slightly different space-time than we're used to, and we don't have any idea of what consistency rules are on this space-time. So we'll have to work much harder to make similar statements in flat space holography, but nevertheless, this is what we'll try to do. Okay, so again, as I said, in ADS-CFT, bulk and boundary unitarity are identified. But here we know what bulk unitarity is from amplitudes, and we'll try to understand implications of this on the CFT spectrum, on the CCFT spectrum, and on the boundary theory. And we'll try to understand, one of the motivations for this is to understand how bulk unitarity can possibly emerge from this CFT description, or what features we must even have at the boundary such that the bulk theory can be unitary. So one thing we know in the bulk is that locality and unitarity are sufficient to determine 3-point amplitudes, and indeed all tree-level amplitudes. And we want to see what the analogous statement is on the boundary, particularly if they imply something about the spectrum and the OPE coefficients in at the boundary. Okay, so let's begin. So this is the outline of the talk. I will briefly give you an overview of celestial holography, and then I will explore some features of bulk locality, and unitarity, and then I will conclude. Okay. Okay. So celestial holography is the statement that there is. So you start with scattering amplitudes, but instead of the usual momentum eigenstates, you transform to a basis of boost eigenstates. And what does it do? This one thing we know is that if you make this transformation, because of the isomorphism between the Lorentz group and the conformal group at the boundary, if you compute correlation functions of these boost eigenstates, they are guaranteed to transform transform nicely under the global conformal group here. So I parameterize the momentum by an overall energy. The plus minus is just the sign of incoming or outgoing. And sigma is the helicity. So this is all about massless particles. So sigma is just the helicity. And this Mellon transform implements the change of basis. And one particle states transform this way. This is just the little group factor, but in terms of the Mobius transformation, this takes this form. And you can convince yourself that if you do the change of basis, this transforms indeed like a conformal correlator. And so in general, every energy, there's a Mellon transform which trades the energy for the conformal dimension delta. And here I want to point out a difference at the outset between flat space holography and ADS-CFT. The conformal dimension has no relation to anything that happens in the bulk. It's as far as we understand, at the moment, it's a free parameter. And one of the open questions in flat space holography is to determine the minimal set of conformal dimensions that is possible, or so delta is not related to the mass or anything like that here. And so this is the situation with massless particles. It can also be made to work for massive particles, but it's a bit harder. So massive one particle states are labeled by the spin S and a spin projection along a chosen axis, and then a massive momentum. And I've parameterized the momentum in this way. You can once again implement a change of basis, but here the change of basis is more non-local. What it does is it collects the contribution from a single mass shell, from the entire mass shell onto a point z bar on the celestial sphere. And I won't present explicit expressions for this integration kernel, but it ensures that this is a state with a definite spin weight j on the celestial sphere. For the simple case of scalars, this is just a bulk boundary propagator, which takes you from one point on the mass shell hyperboloid to the point at the boundary where the hyperboloid intersects null infinity. And so in most cases, I will not write down the explicit integral transform that takes you between the celestial amplitude and the momentum space amplitude. I'll just schematically denote it as an integral. And so I should mention this an tilde is what is called the celestial amplitude. And it could be the external states could be massive or massless, and we will talk about it as appropriate. So far, I've only told you about global conformal symmetry. And this could just be a statement about kinematics. I'm just rephrasing things from one basis to another. But there's something more to it, because one thing we know is that the asymptotic symmetry group of flat spacetime is BMS, which is infinite dimensional. And in particular, one implication of this is that correlators which are invariant under BMS are invariant under a local conformal transformation of the two-dimensional celestial sphere. So this implies that this putative dual CFT has the full Virasoro symmetry and not just global conformal symmetry. But any choice of vacuum spontaneously breaks BMS down to Poincare. And the Goldstone modes of these broken symmetry are the soft gravitons. And the corresponding ward identities that you can write down for these spontaneously broken symmetries have been shown to be equivalent to the soft graviton theorems that were derived by very early on derived by Weinberg, and then a new one much later identified by Strominger and Cacciazzo. So because of this, and the subleading soft graviton is what generates the local conformal transformations on the celestial sphere, and this is related to the CFT stress tensor. And so because of all of this, the conjecture of celestial holography is that you compute the celestial amplitude, which is the momentum space scattering amplitude, but written in the basis of boost eigenstates. And that is identified with the correlation functions of operators on the celestial sphere. And the conjecture is that there is an autonomous structure which governs these correlation functions. And that is called the celestial conformal field theory, or CCFT for short. Okay. So before I go there, are there any questions about any of this? Okay, so let me briefly tell you about how OPEs are computed in this celestial CFT. The earliest, the way OPEs were initially computed was by noticing the following. If you have a correlation function of these operators, and 2 points on the celestial sphere approach each other, Z1 approaches Z2. This is the OPE limit on the boundary. But if you look at what happens in the bulk, the dot product of two massless momenta start vanishing in this limit. And so people identified the collinear limit with the OPE limit at the boundary. And this works. You can read off the OPE coefficients from splitting functions of scattering amplitudes. And things were fine, but there are several problems with this. The first, one of the problems is that you can compute a 4-point amplitude of all massless scalars, which involves a massive scalar exchange. And if you perform a conformal block decomposition of this, you'll see a lot more operators being exchanged. And these are not visible from the OPE because the 3-point the massive scalar exchange does not lead to a collinear singularity of the 4-point amplitude. So it naively, it seems like there's no way to see this from OPEs. And another thing was we showed that OPEs with only collinear singularities tend to be non-associative in generic effective field theories. Things are fine in Yang-Mills or pure gravity, but the moment you add higher derivative interactions, it seems like if you restrict the OPE to only include singularities coming from massless 3-point amplitudes, this is not associative. And so because there was then a conjecture that the OPE is indeed not complete. And one of the additions that was proposed was from boundary multiparticle states. So I just want to clarify that these boundary multiparticle states are a bit more mysterious. They're not literally multiparticle states in the bulk. They're not loop corrections in the bulk. But so this was proposed to be an addition to the to this OPE. And the basic problem is that you see the collinear limit, the dot product of two momenta involves factors of energy. And in doing the Mellin transform, you're integrating over all energies. And so there is a range of integration over which this collinear factorization is just not valid. And so you cannot assume that all the terms in the OPE are given by uh, just by the collinear limit. And another obvious question is if you have two operators corresponding to massive particles in the CCFT, this procedure doesn't tell you what the OPE of these two operators should be simply because two massive particles do not give you a collinear singularity. And so what we can learn from this is that the collinear limit is a subset of the OPE limit, but it's not the entire OPE. And so this is one of the main motivations of my talk. It will be to use bulk unitarity to tell us something about the OPE in the CCFT. Okay, so now I'll move on to part two. Are there any questions? Okay, so in this, in the next few slides, I'll try to understand what the implications of bulk locality are on the boundary CFT. And the playbook here is going to be very similar to ADS-CFT. Again, in ADS-CFT, the fingerprint of this local weakly coupled bulk was the bulk point singularity. So you have 4 points on the boundary, and as you vary the points, you suddenly see that the amplitude diverges. And from the boundary perspective, it's completely um, mysterious. But if you know that there exists a bulk, then you know that when you tune the 4 points, there is a specific configuration where the where wave packets that you shoot in from the boundary will meet at a specific point in the bulk, and this is why the amplitude is diverging. And as I said before, the singularity is perturbatively invisible from the boundary CFT. So that was ADS CFT, but what about flat space? Well, you can write down Feynman-like rules for celestial amplitudes, which are which here I've suggestively made to look like Witten diagrams. So this is the bulk boundary propagator from a point on the boundary of flat spacetime to a point in the bulk. And this q dot, this is the bulk boundary propagator that is written in a conformal basis. Now, these are not Witten diagrams. This is simply the 4-point contact diagram in flat space, but written in a conformal basis. And Q is just is the direction of the null momentum. So because it's a direction of the null momentum, it also picks out a point on the celestial sphere. And we want to ask, where is this singular? And this is something we know very well. You just solve Landau equations for this particular integral. Indeed, it even looks like a box integral. So you can solve Landau equations. And the Landau equations take this form. So each of the propagators must vanish. And in order to make sure that there is a pinching, you demand that omega I, qi sums to 0. But if you look at it, this is literally momentum conservation. And so what this is telling you is that there are a set of singularities that the celestial CFT correlators inherit just because the bulk is the bulk amplitude satisfy momentum conservation. And these are analogs of the bulk point singularity. So just the fact that momentum space amplitudes are supported only on delta functions of momentum conservation translates into specific constraints on the correlators. And what this means is if you put operators at arbitrary points on the celestial sphere, there is no way that you can, in general, satisfy momentum conservation. And so the CFT correlators reflect this. And let me show you a simple example of a 4-point amplitude. We all know that 4-point momentum conservation is only supported on a plane. And the analog of this on the celestial CFT is that this cuts the celestial sphere on a circle. And the 4-point function on the celestial CFT is only supported on this great circle where, and this great circle is specified by the 2D cross ratio Z being equal to Z bar. And so that's why this 4-point function has a support only on this surface. In addition to that, there are these theta functions. And these also make the 4-point function distributional. And if you actually explicitly work out these theta functions, you will see, so epsilon 1, 2, 3, 4 specify whether the particles are incoming or outgoing. So the only non-zero case, of course, is 2 to 2 scattering, where 2 are in and 2 are out in Lorentzian signature. And if you work out the implications of these three theta functions, you will see that the 4-point amplitude, the celestial 4-point amplitude, is supported on patches of the celestial of this great circle. So there's one patch where the cross ratio is between 0 and 1, another between 1 and infinity, and one where it's less than 0. So these are three different analytic functions which are not related to each other by analytic continuation. They're just three different functions which are supported on patches of the celestial circle. And this is a feature which continues to higher point correlators. So again, I just want to say, all we're doing is looking at this condition, and we're realizing that it cannot be solved for arbitrary configurations of points on the celestial sphere. So 4-point functions are pathological in the sense that they're only supported on a great circle. But higher point functions are supported on codimension 0 patches of the celestial sphere, but they are only supported on patches, and every scattering channel corresponds to a patch on the celestial sphere. And if you account for all the patches, these tile the celestial sphere, or they tile a covering of the celestial sphere. And these singularities are reflected as theta functions in celestial correlator. So these lead to distributional singularities. But we know that scattering amplitudes have more singularities than just those arising from momentum conservation. And in the next part, one of the things I will do is try to understand the implications of those, mainly those arising from poles of tree amplitudes, and what the implications are on the celestial safety. But before I go there, are there any questions about any of this? Yeah. Mhm. Right. So yes. Yes, and indeed, omega has we identify it with the energy, and so it is. Yeah, they're not Feynman parameters here, but yes, yes, it has the same interpretation. Um, any other questions? Okay. Okay. So now let's move on to combining locality and unitarity. So this is basic things. Locality implies that tree level amplitudes in position space can only have poles when xij squared is 0, or in momentum space when some subset of the external momenta go on shell. Causality gives you an I epsilon prescription for every Feynman propagator. And what this means is at tree level, the tree amplitudes have imaginary parts, but they're completely distributional. They're given by this identity. But the imaginary part is fixed by unitarity because the residue, whenever some intermediate particle goes on shell, is governed by unitarity in that it factorizes into lower point amplitudes. And so this is the statement I've written here. The imaginary part. So at this point, I'm only working at tree level. So the imaginary part of this tree level amplitude is completely fixed by lower point amplitude. So I've just written it here, and I've rewritten it as an integral over the exchanged particle. And this sum here is a sum over one particle states. But I can rewrite this sum in a different basis. So for example, I can, the thing to do here is to rewrite the sum in a conformal basis. And I can replace the sum over the intermediate one particle states by an equivalent sum in the conformal basis. And depending on whether the exchange particle is massive or massless, there are different there are different identities amongst these integration kernels that guarantee you completeness. So this is the simplest case where there's a massless exchange, and then you just integrate over the principal series uh, and the celestial sphere coordinates and sum over the helicity of the exchanged particle. And for I haven't shown you all of them, but for the case of exchanged massive scalar, the ADS3 bulk boundary propagators satisfy this relation, which ensures that you can convert from a sum over the phase space of a massive particle onto an analogous thing in the conformal basis. So for massive spinning particles, there are identities which are satisfied by these integration kernels. These are related, these integration kernels are related to spinning bulk boundary propagators in ADS3, but they're kind of messy and they're best written in embedding space, and I haven't displayed the expressions here, but similar techniques work, and you can replace the completeness relations by these. Um, and so this, what it motivates us to define these objects called celestial cut integrals. So instead of integrating the entire amplitude, I stick in this delta function, which replaces one of the propagators. So I can define various kinds of cut integrals. So there are massless cuts, where massless two-particle cuts, where I replace a two-particle propagator by the delta function. Of course, I should say that this is, if this amplitude has no singularity here, this is just manifestly zero. So the only case it's relevant is when the amplitude itself has a pole which cancels this. So okay, so and to distinguish between massive and massless, I write the massive cut integrals with a bold, with a bold face, and I can similarly define objects uh, which involve multi-particle poles. So I should again make a distinction between what are in the amplitudes literature called multi-particle cuts, which actually involve uh, cutting multiple lines. But here I'm always cutting just one line and replacing one pole with a delta function. And the only distinction I'm making is how many momenta are involved in this cut integral. Okay. So let's focus on the two particle massive cuts, because so what we're interested here is to look at this cut integrals and try to get some information about the OPE. So let's look at the two particle cut. I have rewritten it here just for convenience. And this n particle amplitude factorizes into a product of a 3-point amplitude and an n minus 1-point amplitude. Now I assume that the exchanged particle has some spin b, some spin s, and b is just the projection of that spin onto the z-axis. And as I said before, I can replace this the intermediate sum over intermediate states by an equivalent sum in the conformal basis. And so there's an integral over the principal series and the two coordinates of the celestial sphere. So this is a statement about celestial amplitudes. Now I can use the dictionary I told you about before, and I can replace all of this. I can rewrite all of this in an operator language. So I've written cut here, but it's this should be understood as the imaginary part of this celestial amplitude coming from a certain exchange. And so rewritten in operator language, what this means is the imaginary part of this correlator is given by a certain integral, which looks like this. Okay. So I've rewritten it here, but and this already looks very similar to this the shadow formalism of conformal blocks. What it's doing is picking out the contribution from some primate operator and all its descendants. So right now it looks like this is a formula for, this formula might just give you the contribution to maybe just give you the imaginary part of the OPE coefficient or something like that. But what you can show is, as long as you assume usual things that you assume about OPEs, specifically that all other insertions are far away from the two operators that you're OPEing. And you assume some things about the OPEs between two incoming and that the OPE of two outgoing only has one outgoing operator. You can show that this actually gives you the full OPE. And you can also use this to actually read off the entire OPE, not just the leading singular contribution, but all of its Virasoro descendants, so the left and the right. And here I've just written the leading singular term, but it looks like this. You can evaluate. So this is for the specific case of a scalar, and this is arising from the 3-point amplitude of two massless scalars and a massive scalar. And this beta function just comes about from this 3-point amplitude. And this integral formula packages the contributions um, from all of the this packages contributions from an infinite set of operators on the boundary, because this is an integral over the principal series, but the contour can be modified to pick up the poles of the beta function. So I want to pause here to just emphasize what this formula means. In the bulk, you just have one massive particle which is being exchanged. But if you interpret it from the boundary, there are now an infinite number of, there's an infinite tower of particles which are being exchanged from the boundary perspective. And so unitarity in the bulk is kind of dictating the set of operators that are consistent with this massive exchange in the bulk. And so this is one of the things that we were trying to understand. Okay. And you can easily extend this to, that was scalars, you can easily extend this to arbitrary spinning particles. You can just write down the 3-point amplitude with two massive helicity sigma particles interacting with a massive spin J particle. This is this. You can compute the corresponding 3-point amplitude. It turns out there's a standard coordinate dependence that you expect from a 3-point CFT correlator. And the OPE coefficient here is a beta function, which depends on H and H bar are delta plus minus sigma by 2. Depends on the conformal dimensions and the spins. And so this 3-point amplitude now determines the OPE of two massless particles with OPE corresponding to this. And as I said before, all of its Virasoro descendants. But the advantage of this formalism is that it's no longer tied to collinear singularities of bulk amplitudes. And so you can use this to extract any OPE you want. You can consider the OPE of an amplitude involving one massive and one massless going to another massless. You can consider all three being massive, and you get the corresponding OPE coefficients and a prediction for what operators are exchanged on the boundary from this. These expressions are not nice, so I haven't written them down here, but you can compute these 3-point celestial amplitudes, and they give you predictions for what this OPE looks like. Okay. Okay. So, are there any questions about this? Yes. I don't know how, just from this, you would, without the knowledge of the non-singular terms of the OPE, I'm not sure how you would directly check the associativity, because this involves 3 operators. So yeah, I don't know any direct way of checking it. You can check the crossing symmetry in the, when I say crossing symmetry, I mean it in the sense of the CFT. You can check crossing symmetry, but the statement of equivalence only holds as long as you know the entire spectrum of the CFT. So That was about two particle cuts. We can generalize this to cuts involving more than one particle, more than one particle in the momentum. So you can define this three particle cut. Here, I will focus on the three particle cut, uh, which arises from a massless exchange. And so this factorizes into the product of a 4-point amplitude um, and an n minus 3-point amplitude. And you can repeat the same trick of exchanging the sum over exchange states with um, rewriting it in the conformal basis. And what this gives you is a formula for the 3 OPE. So this is a formula when 3 of the insertions on the celestial sphere are closer to each other than to any of the other insertions. And so this, you can evaluate it, you can compute everything, and it gives you an Apple function, Apple F1. And the arguments A, B1, B2, C are written here. And there are two other terms which are permutations of this, which I haven't written here, but are indicated by the dot, dot, dot. Perhaps the most surprising feature of this is that this is not what you would get by applying the OPE to two operators consecutively. So I can take O1 close to O2, O2 close to O3, or the other way around. But that is, you certainly don't get an Apple function by doing anything like that. And the one way to interpret this is that this is giving you more information about the spectrum. This is telling you that the 2-OPE missed some contributions from some new states on the boundary. And we must include those in order to. So once again, what's telling you that this 3-OPE has more information than just the OPE that we wrote down before, which means that the 2-OPE was missing some terms. And by one hope is that we can look at this and try to identify the new operators that are exchanged. And along these lines, there was a conjecture that the new states are related to multi-particle states on the literally multi-particle states on the boundary. So these are, in some sense, analogous to multi-particle states in ADS, where you have two operators, with the normal product of two operators. But because the state operator correspondence works differently in CCFT than in a regular CFT, this it's a bit unclear what these states are, but the hope is we can study this OPE further and try to understand, try to make more predictions about what these are, and also compute correlation functions these new operators. Okay. So let me just end by summarizing what we looked at. We looked at fingerprints of bulk locality and unitarity on the CCFT correlators. And we found that locality forces the CCFT correlators to be distributional, and these are theta function distributions. But there is more than that, because the amplitudes have more singularities than just the ones given by momentum conservation. And one of the things we saw was that in the guise of factorization of amplitudes, they seem to have non-trivial implications for both the OPE and the spectrum. Now, because the conformal dimension in ADS-CFT was directly tied to the mass of the particle in the bulk, there was it was not hard to believe that there is some constraint on the spectrum in ADS-CFT. But here we see that this somehow comes about in a much more non-trivial way, where factorization forces you to have specific combinations of operators on the boundary. And if you demand that there is a consistent structure which actually reproduces amplitudes, we are forced to make assumptions about what the structure, the spectrum of the boundary CFT is. So apart from all of this, you can just, one of the things we showed was that factorization in the bulk gives you a powerful new way of computing OPEs without having to rely on collinear limits of amplitudes. Multi-particle states signal new operators in CCFT. The outstanding question is whether we can identify them. And finally, I just want to say that this formula is very reminiscent of the of a formula for the loop level collinear limit derived from unitarity cards in these papers. And so this opens up the possibility of extending this kind of analysis to all loops. So thank you. Any questions?
Thank you, Akshay, for this very nice talk. Do we have some questions?
So I may have misunderstood, but you said you access massive amplitudes or just massive intermediate particles?
Both.
Right, you do, and this. So if you detect them in the celestial CFT, presumably you also detect them in the Carolean one too, by Mellin transform, or is does something go weird there?
So we don't know we only understand the connection between Carolean and celestial when the external states are all massless. You can certainly take something which involves a massive exchange and just compute the corresponding Carolean amplitude.
Mm-hmm.
But beyond that, when the external states are actually massless, are actually massive, because they don't actually reach null infinity. I'm not sure how a position space holography should be framed. Here in the CCFT, it's kind of non-local because it collects all the information from the entire mass shell at one point on the celestial sphere. We're thinking about things like this, but
But maybe you're getting stuff coming from U equals infinity in the celestial CFT that's not visible in the Carolean CFT. Is that, roughly speaking, one way of saying it, or? I mean, there are contributions at U equals plus infinity, which is where the massive particles would go.
I'm not sure because this the way it's done here, everything is focused at U equals 0. There's just one cut of sky.
I see.
The intuition here is that you're in boost eigenstate, so massive particles are infinitely boosted and they're very similar in some sense to massless particles. But I don't know what to make of it in a position basis.
Okay, no, it's interesting. Yeah.
Any more questions? So in the ADS case, I mean, you can get quite a lot of good results if you focus on operators with high spin, right? And you could do expansion around high spin and do really perturbation theory. How does it work in this case? I mean, can you gain something just focusing on these operators?
So I guess there's the intuition that for very high spin, there's these generalized free fields. Here, I haven't thought too much about it, but again, right now there's nothing pointing to the fact that there is something simple at very high spins. But that's all I'm
thinking. Yeah, that's probably is an interesting also direction of.
Yeah, but maybe one way of understanding this further would be to start from ADS CFT and then try to take the flat limits like in the previous. What that implies celestial CFT. But that's something I've done, but it's worth it.
Thank you. Any more questions? If not, let's thank Akshay once more.